локальный правый.
Угу.
Можно, почему это марксизм обозначает через норму? В смысле, это просто обозначение или это вещь?
Скажите что-нибудь.
Раз.
Да, слышно меня.
Спасибо большое.
Ну,
Можете, пожалуйста, аккуратно все сложите и туда в 32 отнесете.
Да, конечно.
хорошо. Лучше трейс держать в голове, потому что можно так циклически перетаскивать. Но я выбрал обозначение absolute value. Не знаю почему.
Да, все можно.
Ага.
Камеру вы проверили, да? Там видно нормально.
Да.
So let me continue. We want to describe Goldman bracket today, and now I just say what is a fundamental group of a surface with boundary. I defined some set of homotopy classes of free-oriented loops, which is isomorphic to this quotient z pi1 mod the commutator. I defined the surjection, and now I consider examples of elements in this set. For example, in this sphere without three points, or torus without 1 point. Its fundamental group is again generated by two elements, and remark again we can. There is an example where we can explicitly compute this group, as in this example. Let's consider a torus without boundary. In this example, this set is just, it is again infinite dimensional, but the set of generators are clear. It is a to the power n, b to the power m, and m are integers, and a and b. This is a loop which goes, say, n times around this loop. Yes, and then it goes m times such loops form a basis in this set, in this vector space. And now let me formulate. What do you say? Torus?
It's a punctured torus without a point.
No, this one.
No, this without boundary.
Closed torus.
It's closed torus. And we have an abelian fundamental group, but somehow. Okay. No, I don't understand.
Because
This is just example out of our setting initial. But
So I think the point is that even when you start with different surfaces, this space of combinations of homotopy classes of loops can be the same for different surfaces.
Yeah, in this example and in this.
Because it involves this relation where you mod out by commutators. So even something non-commutative becomes commutative.
Okay.
by the way, I don't quite understand all these three equations.
inequalities, can I just think that this algebra is just group algebra of first homology?
Group algebra of first homology group.
Of abelian group of first homology descent.
No.
In general, no, I think. Just a second.
I know that the first homology is a abelianization of fundamental group.
Yes, so the question is whether the abelianization of the algebra of abelianization is the abelianization of the algebra.
It's, I have to think, I don't think it's,
But maybe it's obvious in case of free group.
yeah, I mean, I think it's possibly just accidental to these examples. Let me think.
Just because in the general setting I don't understand equalities in this definition, so I understand what means the last. Maybe I understand last equality, but I don't understand first equality.
Why homotopy classes or
Yeah,
conjugacy classes?
Yeah, just because.
It's because in the you can change the base point. So when you fix pi1, you fix the base point.
Yeah, here we
And when you take free homotopy classes, you
Choo-
don't fix the
choose the base point.
And so when you try to do, like, draw a path from one base point to the other and come back again,
Yeah, but somehow I identify in the first definition two circles which join it by some. Right? But maybe it's questions are not important.
Think about about this set as
Yeah, well, what is not obvious in this definition that this is algebra, for example. But I can think about the last definition. It's okay.
none of them are algebras. So far, they're just abelian groups. They're not algebras.
So what's quotient means to the last?
So the top part is an algebra. The group algebra is a non-commutative algebra. And then we form a subgroup of it, which is the subgroup of all commutators. It's not an ideal.
Okay. Okay.
And the reason you do this is think of the trace map from the algebraic matrices. It vanishes on this kind of thing. So this is the source for a trace map. Why did you assume that the boundary was non-empty? That's not going to be important, is it?
it's not really important, yes. This is more general setup. Then I want to formulate a theorem of Goldman which is about this map. This map, it is well defined. Lie bracket on this set G of sigma. And what we need to show,
I don't understand. what is the well-defined Lie bracket? I didn't think you defined a bracket. You're saying there is a well-defined Lie bracket. Are you going to give a formula for it? Or?
Oh, I mean, yes, I skip very. I didn't define it. We have the following bracket. It is from 2 second wedge power of this g of sigma to g of sigma commutator. If you have two say alpha and beta, two homotopy classes, modular commutator. Yes, then it goes to the following sum. Let me write and then I will explain. The following sum of if we have two locally we have loops, but locally we have crossings of these loops, and then this sum is over points of crossings. And what is this? This is a loop, new loop, which is what? If I go first is alpha, yes. I go like this, and when I meet this point, I resolve this singularity. And I go like this. This will be.
Where's the solution? Where's the solution?
This is a local picture.
Нет, просто одна стрелка обязана входить, а другая выходить. Вот налево.
No.
I mean, one of them is first and one of them is second. And so you just need to give a rule to say what's a positive and what's a negative intersection.
Yes, let me orient the surface counterclockwise, and if the question about what this part, do you understand what will be this element? This is a.
There's no smoothing if you want to define this, right? It's a concatenation. It's like run double time around alpha, starting at P, and then double time around beta, starting at P. And then that's a loop. No smoothing.
Maybe I don't. Let's in example of torus, maybe show in this example.
It's just like the composition in the fundamental group, except now the base point is moving.
So why do we need to resolve the intersection then?
Why what?
Why do we need to resolve the intersection?
We don't.
Oh, okay, so we just
So you just you assume that alpha and beta intersect generically. So all the intersections are transverse. And then at each point of intersection, you run along alpha at double speed. Once you come back to P at that point P, and then you run around beta at double speed from that point P and come back to P, and then you consider that as a single loop. So it's just like as if you were doing composition of the fundamental group at base of P.
Mm-hmm.
Or maybe the convention is the other way. I don't know who comes first, beta or alpha.
Who comes first is written here as if alpha.
First alpha, then beta.
Yeah, first alpha. And
It's just the composition in the fundamental group base of P.
yes, so in this example of torus, what is happened? We go along alpha, and then the alpha, then we go around beta, and then we have a loop, new loop, which I denote by alpha.
But why are you splitting them apart?
Why I
There are no gaps there.
Strange, because now we just got a loop that is homotopy to alpha. To the
It seems that this summand is just is equivalent in this quotient to I'm stupid. No. But all the summands are the same. That's what I don't understand.
But there's a sum over intersection points.
Yeah, it seems to be up to sign. It does not depend on the intersection point.
Does the signs change from point to point? So it's not like a sum of everything with the same sign.
Okay. Okay.
Because there are positive intersections and negative intersections.
Okay, but summands are the same.
Up to homotopy, is that true? I'm not sure.
Just as you say, just change your base point, but it's the same.
I'm not sure.
So basically this sum is just some loop taken with some coefficient. That
No,
can be
I'm not sure that it is, because,
Yeah, my question was, does this summons up to sign are equal in our question or not? This is the question, and it seems for me that there's this.
No, I would say no. They are not up to gamatopy. Even up to gamatopy, they are not the same. If there is many points of intersection.
Yes, but your construction says exactly that this is the same loop, just started from an intersection point.
no, I don't think so.
Or maybe your resolution.
I don't think so.
I don't know.
What is then do we resolve the intersection or do we not?
We do not. Don't draw.
In my text, we resolve him.
I mean, maybe it's homotopic after the fact, but this has to be justified.
So I understand how you can obtain different loop. You just have to write your sign as coefficient of, say, alpha. or something like this. You can change sign of counting one of your two loops, and then of course you obtain something new. In your definition, it's the same.
Let me say firstly what is this signs. This is -1 or +1. This is the orientation of sigma modulo we see on this, this is alpha, this is beta, yes, and if alpha turns counter clockwise like that, then this will be the opposite to the orientation of a surface, and epsilon p is equals -1. Yes, orientation of basis E1, E2. Who are they? If we have this picture, we have intersection points, and we have two tangent vectors. If this is alpha, this is beta. T, P, beta. Yes, here. T, P, alpha. Two tangent vectors. Okay. And why this is, for example, anti-symmetric, skew-symmetric? This is obvious, I would say, but the only place here which depends on who is first, who is second, is this sign, yes, and if we had beta and then alpha, then we have extra sign. Yes, let's see. We have alpha and beta. If alpha goes first, then we resolve this alpha. What sign we get? We will get two homotopic curves, but the sign will different. Yes. And if alpha goes first, then we have sign -1 in this situation, epsilon p -1. But if we go firstly beta, yes, then we turn in another direction, and the sign is +1. And this holds for every intersection point, so this is anti-symmetric bracket. Then it is clear that it is linear, bilinear in both terms. This is also clear. It is not clear why I claim that it is Lie bracket, and it is well defined. So we can. Let me first say why it is well defined.
I think I have an example where it really does matter enough to homotopy what the intersection point is for the composites. So I'll let him finish
y well defined. What we need, say if when I compute this bracket, I choose, I did not say it precisely, I choose smooth representatives of these classes, firstly, which intersect transversely. But I could choose very different representatives, and it is not clear why the bracket is the same when we compute it on another representatives. And but let me show that, say if we have locally the picture like this, we have two intersecting points, P and Q. My argument will be in three steps. Firstly, we consider such situations, and this is clearly homotopic to this situation. Yes. Here, A prime, say B prime, A, B. But why the bracket is the same? Let me, I would write like this. Absolute value A and B, and I compute the commutator by this rule. Let me compute this for these representatives. Well, we have 2 points. Yes, and we resolve one and another. We have 2 summands. We have epsilon P, A prime, P, B prime, plus epsilon Q, A prime, Q, B prime. But this epsilon P is 1, this epsilon Q is -1. Yes, according to our rule. Yes, what is written? We first summand is like that, with sign plus, and we subtract the homotopy picture, which is 0. But and in this situation we obviously have no intersecting points, and in this situation the bracket of alpha of A and B is also 0 by obvious reason. So these 2 things are equal. Bracket does not feel this difference. Let me. And the second step is to show that if we have another move, say if we have triple intersection. And we, yes, say A, B, C, B. locally the picture is like this, and this is clearly homotopic to we can push this line down. Yes. No. Yes, B and A are unchanged, but C is C prime. Why the bracket does not fill this difference? I claim that, yes, I claim that if we have C, then commutator AB, this is the same as C prime AB. Why it is so? This is what we need. Well, let's compute. We can compute just left hand side, right hand side, and see that they are equal. We can believe this, or we can prove.
I can't read what's written there. It looks like the same thing equals the same thing. Or is there a C and a C prime?
C prime.
I see. So you're trying to move past the crossing. Okay.
Mm-hmm. Push down this line. Well, let's see. Consider left hand side. The first step, we resolve this point. Oh no, let's resolve this point. We will have such picture with the sign plus 1. Then we resolve these 2 points. This thing we computed this commutator, then we compute the whole commutator. Left point gives us minus. And the second point gives us знак plus. Two summands. And right hand side is very similar. What we do, we resolve firstly this point and then these 2 points. This goes again with sign plus. Then we go the first summand is this. We resolve the left point plus minus 1. So what we see, the pictures are equal. One is equal to another. This equals to. They are all homotopic to each other.
I still don't understand your resolving of the singularity. Your claim is that after you perform the composition at this point, the result is homotopic to something that splits off like this? Like, why do you get to resolve this crossing?
Why?
It's not homotopic because there was an example with the Torus where
It could break up into 2 components after resolving, for example. Doesn't look like
yeah, but in this example, if we resolve, we get just a loop which is common topic to one of the loops we started from. So it's very different from composition.
So I don't understand what this means when we resolve the singularity.
You think that we can get two components.
Sure. And then am I supposed to interpret that as a sum in this group? I don't know. So maybe the assertion is that these two things are equal modulo these commutators, but why?
Could you give an example when we get two components?
Well, imagine two loops that just intersect at a single point.
Like this?
Yeah.
But they will not be transversed.
That's why not?
I mean,
This is
not
a,
like this.
this?
But a picture is two-dimensional. So
No, but I
Yes,
thought you were,
if they intersect at a single point, they must, if they're smooth, they must be tangent to each other.
No, we're not drawing it on a plane, we're drawing it on a torus.
Ah, okay. Sorry.
but maybe then I don't understand what you're, when you resolve, you just lift, you don't like cut like that. You just lift them apart.
No, we're cutting now.
I mean, you could cut and then re-glue, or you could just kind of pull them apart. So which are you doing? It looks like when you went from this picture down here with C on top, and then to, you said left-hand side, it looks like you're coming in along the bottom, along B, and then going back down along A. So you're like cutting in, going like this. And when you do that, it does seem like you're gonna get two components, which is maybe fine. You interpret that as a sum.
I thought that we get namely one component. Why it is so?
Maybe you do, according to this rule, if you have two of them, and they're distinct, A and B, and your rule is, I don't know, I'm coming in along B, and then I go out along A, and then as I go back around A and come back, I do the opposite. So it's like, I get half of B, followed by half of A, followed by half of B. So it's like one continuous.
Let's see on this example.
But that's a single, is that supposed to be two curves? If those are two curves, then they're not intersecting transversely. If it's one curve, it's intersecting itself transversely. So yeah, if it's one curve intersecting itself transversely, you probably don't allow that. You probably assume alpha doesn't intersect itself.
Yeah, let's, I don't know. In your example, if you have your example,
I think in my example, you're right, that if you do it in the way you proposed,
Actually, there is
it's a single component.
this point, P, Q. We alpha, beta. If we go alpha, first we have this point, we turn to beta.
yeah, the reason that you always obtain one loop is that you must going along whole first loop and then along whole second loop.
Yes, if we firstly go, we choose a point, intersecting point, we go through alpha, and then if we again see point P, we turn to beta, go along all beta, and then turn to alpha.
Okay, I think I see now. I think it's okay.
I'm sorry, I did not.
No, I think it's okay.
Did not.
I think I understand the claim now. Yeah. So it is what I said, or what you said. You start at P, you go all the way around one of the loops, come
Mhm.
back to P,
Mhm.
all the way around the other loop. And then that's the definition. And the second claim is that that's homotopic to this smoothing in this way.
Mm-hmm.
You just kind of, when you come back around to do the composing, you kind of pull apart the intersection.
Yes, I definitely did not think about this so much.
Okay, so that's the fact that for triples, the bracket is well defined.
For triples, yes, this is clear. If this is clear, then we note that we have a class of a trivial loop. A class of a trivial loop, and I claim that it is unit in this J of sigma. Class of trivial contracted loop. Y and the commutator with any alpha is 0. Why it is so? No, the argument is very easy. If we have alpha locally, if we have this trivial loop which intersect it in somehow, then up to homotopy we just move this trivial loop away from alpha, and now they just don't intersect. So the bracket is 0 when they don't intersect, and if we show that the bracket is unchanged, if we choose another representative for the loop, the bracket does not change. So this commutator is 0.
So because this is going to be a Lie bracket, it means that there's a preferred central element in this Lie algebra.
Yeah, this element lies in the center of this.
So what were you going to say next?
The Jacobian identity.
And then after that, I wanted to give an example where you can see how the base point matters.
Yes, the main difficulty why it is well defined. The third step is simple. If we have two such steps, then we do this many times, and if the curves are homotopic, then after some finite sequence of such steps, we will homotopy one curve to another, and bracket does not change due to these steps. Jacobian identity. How it is look like? suppose we have three elements, gamma 1, gamma 2, gamma 3, and we compute triple commutator plus gamma 3 gamma 1 gamma 2 plus gamma 2 gamma 3 gamma 1, and I claim that it is 0 for any curves gamma 1, gamma 2, gamma 3, and idea of proof is the following. The argument is to consider the picture when all three, to analyze local picture, and then to show that if we have a picture like this, and we apply, we compute commutators, then the summands will contract each other in pairs. The sign will come up in such a way that all terms will contract each other, subtract each other. Gamma 2. Let me show in this situation what is going on. So let me denote this point P2 primes. This is P. Yes, and what we do, we see. Let me see firstly two summands. Firstly, we compute gamma 1, gamma 2 commutator. We see this point, just one point. We resolve it. What picture we see? This. Yes, and this goes with sign plus 1, and then we resolve these 2 points. Let me resolve this point. Say P prime. This picture. What is this? Is gamma 3. And this curve is what I denoted is gamma 1, gamma 2 at point P. And the next step, we resolve these 2 points. This will go, we see. This is we resolve this P prime, and this will be, and here will be the second term. This one. Let me don't write this term. Let us see that this summand will be subtracted by summand with here. Here we firstly compute commutator gamma 3, gamma 1. What we get? We get this picture. Gamma 3, gamma 1. This point. Resolve this point. And then this goes again with some sign plus 1, and then we resolve, say, this point, and we will get sign minus 1. Minus 1, and the picture is the same as as this. So these two terms will subtract each other. This term. We resolve this point, and we get sign minus 1 and this curve again. Homotopic curve. So these terms cancel out. And in another, if we write down another terms here and here, they will cancel out with terms which come from here. So in this local picture, all summands cancel each other, and in general this is just local picture, and this is true if we change the orientation. So these curves we can change another, but the sum will again cancel out. But globally, this will be and globally the situation will be the same. Yes, maybe questions?
Shall we make a break? Do you have how much more material do you have?
Maybe this is the final of a proof. So
Is this it?
maybe yes.
Do you have an example where one can fully describe the bracket, or like in a basis?
We can compute something.
Can I ask a question? In the beginning, to assume some stuff on, for example, fundamental rules of some condition, and you haven't, I think, used them. So where have you used these conditions? Because I think these work for general case.
Which conditions?
For example, the valency of boundary, or you assume, for example, the fundamental group must be the free, or the boundary must be some n component, or something like this. I don't need anything.
It's not necessary.
Yeah, really what you need to have is oriented surface.
Yes, because orientation is not that.
Maybe this boundary, maybe this other.
I don't know if I'm missing something, but it seems.
So let's after break, let's try to compute some brackets.
Yeah, maybe I understand.
It's maybe an example, maybe not, but
Yeah.
it's kind of hard to tell if things are homotopy or not. But if I go back to this three-fold torus, three-fold sphere, and suppose I have type 2, so there's a gamma 1, or something very simple. But gamma 2 goes around both holes.
Yeah, this great example it should be works because this non-trivial.
So I think if I write these as compositions of generators for the fundamental groups,
Yeah.
this would be alpha. This would be what? From the point of view of here, it would be beta, followed by alpha. So if I write it left to right, it would be beta alpha. But if I write it from the point of view of this one, then it would look more like alpha than beta. Okay, I screwed them up, but yeah. And so it looks like you would be like alpha alpha beta versus an alpha beta alpha when you do the two compositions. It's not obvious to me that they're homotopic as free groups.
Yes, but it seems that the general reason why the point matters is related to the fact that you don't usually have group structure on conjugacy classes.
Right.
And but in our case, when our group is free, it's I don't know if it is true, but it's related to my first question. Is it true that these quotients yeah, is it true that this is just incidentally group algebras of first homology? In our examples, it was true, and this surely means that on the conjugation class there is group structure.
So let me try to remember. I need to think what so there's something special that happens here, which is that all these surfaces are K by ones.
Mm-hmm.
And then
So why is it clear that with like swap optimization in algebra group,
I'm not sure what it is.
even for surfaces, even for closed surfaces, right? I mean, if we have a free group, okay, I believe in it, but if we have
Yeah, it's question of on free group.
but no, of course we have surfaces where
So I think
it's not.
Say boundaries on it.
No, it's not that we don't need necessarily an boundary.
Yes, but I just want to understand. Am I correct that in the case of non-empty boundary, really, maybe this is the case that all. But so I need to think about this example. So I think this so I have some contradiction in my head and can't say what is it. But in this example, we already saw that it is the case. This quotient we are working with this group algebra of first homology. So this.
Well, that's a basis, but the bracket depends upon the homotopy type of the surface. And so for a torus and this one,
Yes.
they have the same underlying space of free loops,
Yeah.
but the brackets are different.
Yeah. Okay. okay, but I have more basic problem here that so it seems that conjugacy classes of loops here form a group.
No, I think that was one of the reasons why this example works. If we change base point, one loop changes to one prejudice classes and another changes to another prejudice classes.
Yeah, that's exactly my competition.
I don't see why it's
Yeah, and so that's something. Yeah.
I hope so. It will. I read наивно, но что в случае, когда группа свободна, это то же самое, что групповая алгебра просто первого гомологии. То есть групповая алгебра — такой свободный абелевый групп.
Мгм.
То есть, что это всегда будут как бы такие лораны.
Ну, вопрос как бы, что вот P1, взять групповую алгебру вот такого фактора, да? Значит, вот такого фактора, значит, и вопрос.
Да, что это равно ли фактору, вот, да. Ага.
Ну, а здесь у нас сколько? 6 петель. Раз, два, три. Потом вот такая.
Ну,
Вот такая.
Не, ну в каком смысле? Это просто букет трех окружностей. То есть,
Ну да. А, три этих образующих.
ну, в смысле, то есть вот для двух это точно, да, правильный ответ, да, что это будет лораны такие?
Угу. Окей. А в степени n, там, b в степени m. Здесь у нас как будто А, Б, С есть
Да.
в степенях там m, n, k. Будут ли это лораны в этом случае? Да?
Мгм.
Не, а что нужно проверить, что как бы что А коммутирует с Б, Б коммутирует с С коммутирует с А.
Мгм.
То есть если это так, тогда будут лораны.
Нет, ну, в общем, пример такого. То есть, естественно, отображение вот оно есть, оно всегда селективно, но вопрос, не будет ли эта штука чем-то больше. Нет, это просто, ну, мне лично даже для двух это удивительно, потому что это означает, что на классах сопряженности
Структура группы.
на линейных комбинациях классах сопряженности, да, есть такая структура, как на групповой алгебре, как эта группа настоящая. Это удивительно, это как будто говорит, что на классах сопряженности есть структура группы.
Ну, что поменять, как бы взять там один элемент в фундаментальной группе, его сопрячь чем-то, каким-то путем, значит поменять точку,
Нет, ну правильно, да.
Поменять
Когда ты
базисную
говоришь
точку.
про классы сопряженности, у тебя есть два элемента, ты их можешь просто по-разному сопрячь, когда ты перемножаешь. Это, вообще говоря, это не равно альфа-бета, там что-то.
Угу.
Вот, но пример для свободной группы с двумя образующими как будто говорит, что это так. Честно говоря, ну то есть я не соображу, как это вообще возможно.
Так.
Нет, ну сейчас. Нет, ну сейчас.
А что вот это такое? Это какой-то путь.
Не, ну тут не важно, это просто про группу. То есть вот у тебя был представитель класса сопряженности, вот.
Я понимаю, хочу, чтобы они.
Да, ну нет, это утверждение о том, что как бы ты не менял представителя класса, ты всегда будешь оказываться в том же классе сопряженности, когда ты будешь брать произведение. Но это, конечно, вообще совершенно не так. Но для свободной группы сейчас, а может это очевидно? Нет, не очевидно. Нет, вообще не очевидно. Не очевидно, нет. Ну вот как будто твой ответ он говорит, что это так. Или я что-то не понимаю.
Давай попробуем в этом примере, когда у нас есть Тор. Выберем какие-нибудь два, ну вот А и Б, значит, и сопряжем их.
Это скорее про Тор с дыркой или про сферу с тремя дырками.
Ну, а про просто Тор. Это
Ну, просто Тор, здесь нет никакого утверждения, там...
понятно.
Ну, просто она уже абелева, там, класс сопряженности является.
Ну да, ну давай возьмем тор, значит, дырку. Ну вот как бы был этот пример, да, ну там у нас возьмем две петли и их как-то по-разному сопряжем. Значит, вот первая петля. Можно это как-то попробовать сейчас сообразить? Вот вторая петля. Давай они вот так вот. Непонятно, наверное, ничего нарисовано. АБ. Значит, и их вот сопряжем А с помощью одного пути. Какого? Например, вот такого вот, который идет вот отсюда, вот сюда. H. То есть рассмотрим как бы H минус 1, а H. То есть это мы просто сдвинули его, значит, вот эту точку, сдвинули сюда и рассматриваем петлю, вот, которая идет из этой точки. А возьмем теперь какой-нибудь H с волной, который вот что-нибудь мы поймем, интересно.
Нет, бессмысленно рисовать картинки, потому что это пока просто отношения в свободных группах, это две, но они сопряжены, да.
Ну, возьмем, умножим вот этот элемент на этот, когда ты хочешь, чтобы это было там что-то, какой-то G минус 1, G минус 1, да? Что-то G. Тогда это будет так. H. Ну вот, значит, свободная группа, вот.
Ну да, нет, ничего интересного.
Так.
Could I take the hygiene separations if they were taken?
Sure. Let me see if I can log in and change it.
Okay.
What's your name?
Or maybe I just checked the paper on hygiene separations, and I think that I like it, but
It's also in those notes at Cohen and Buttermilk.
yeah. I've seen it. And what is the Goodall-Jones theorem about?
Goodwillie-Jones, it says that the homology of the free loop space is the same as the Hochschild homology of something. So
Okay.
you have to define what that something is. But if the space is a k pi 1, then that something is just the group algebra of pi 1.
Okay. So so maybe I would take hygiene separations, but if the Goodwillie-Jones will be free at the moment, if I decide to change, I
I think
change.
it's free for now.
Okay. Yeah, so I'll just check out what is it about, and
Okay, well, why don't you write to me to remind me?
okay.
I wanted to ask what to compute, what we can compute.
You tell me. Is there an example you understand?
I did not try it, for example, in these lectures. Maybe we can online compute some brackets.
do this exercise. So to do it just for a torus. So we could try to see what the formulas are here.
Some linear combinations.
Yeah, so explicitly we could try to work them out.
We can try this sort of. This will be just linear combination, not. But in this we will have some. What we should see. We will have I times k summons. But summons are homotopic. And
then we should see coefficients if the summons are homotopic, right?
we'll have some curve and the coefficient, and we need to compute this coefficient.
I guess so. And we can do it for low I and k, small I and k, just to see what's going on. So should we try this?
Okay, let's try to compute example. Example, when we have torus, we have two generators of pi1, A and cycles A and B, and have A and B, and in this case, J of sigma, as we said, is generated by monomials A to the power n, B to the power m. And let's try to compute brackets, say A and B, firstly. Say B, A. So we have, up to gammatopy, we have just one intersection, this point, and if you go alpha A, you'll get this loop, just one loop with sign. Let's orient them in such a way to get sign plus. So just one loop with sign plus. Then compute A to the power I with B. This means that we go I times along A yes, and then another loop with B. So we have I'm intersecting points. So we have I summons here, and all of them will be with the same sign, I think. Plus, yes, so I would say that this is I times commutator A and B I summons which are proportional to this curve. Or no. Which are proportional to the curve a to the power I minus 1. We resolve firstly this, then the second summand will be when we resolve this, then this. But they are all homotopic, and they homotopic to a to the power I minus 1.
So in Torus we have an action of the three algebra by derivations on commutative on the group algebra. Right? Do we have something similar in other cases?
No, because in general it's not a complete algebra.
But we still have a representation of the algebra.
Well, the algebra always acts on itself by derivations. As the adjoint representation.
Yeah, but I mean that here we have an action on the
So if so, then repeat the argument. And I would say that we will get I factorial A commutator B. Just repeat the argument. I don't know the answer, but it seems to be like that. Then compute this commutator. And what we get we go I times along A, and then J times along B. We will have I times J summons all with sign plus, I guess. Let's first let's try to resolve this point, and we will get how much time. Let me draw this. We'll see this picture. I don't need to draw another.
I can't see what happens in general. Maybe we can just divide these two j equals to.
Yeah, let's try to compute this. Go 2 times along this and 2 times two times I see 2 points, yes?
Shouldn't there be 4 points of intersection?
Yes, I can't draw it. This. And then one, two. I don't see these 4 points. Could you draw it?
Are the curves allowed to intersect themselves or not? As long as they intersect themselves transversely. I think they must be allowed to intersect themselves because you can compose a curve with itself, right?
I draw a wrong picture, yes. We have A which goes 2 times around. This is A. And then another curve is B, which goes 2 times around.
When you come all the way back around, let it intersect itself. Let it cross itself to close it up. I think that's okay. Is that not okay?
Otherwise, for some curves, we won't be able to get a transverse connection.
So,
No, the curve should not intersect itself.
But they intersect itself. Like it's just the intersection is on the back of the torus.
Yeah, how to draw it properly.
I'm mistaken, but there are classes that can be drawn without
Yes.
self-intersection.
It's true.
So you have to also. Also, I don't see the problem with self-intersection.
so let me just check what is said in these notes.
We don't allow curves with self-intersections.
But it won't resolve them. Like they will just stay there. I think that it just doesn't have any problem with the described construction.
Also, we are taking only the points of intersection between two curves, so you don't need to know what happens with the rest of the curve.
Yeah.
Yeah, we always look local picture. So let's in this example, yeah, we have 4 points.
So I don't know, she doesn't say that the representatives have to be simple. And I don't see why they have to be, or why they can always be chosen to be simple.
Yeah, I also did not saw such conditions that
So,
curve does not have.
self-intersection.
Yes, it may have.
Okay, so that's fine. You could do the same for alpha, but also,
Yes, we have A and B. Let's try to compute this commutator. Then consider A squared is first. We go. We will have 4 summands. Yes, 4 summands. What picture? And with signs, with equal signs, I would say.
I'm thinking, look, since we're allowed to have self-intersections, when I write an expression like this, like b to the power j, I think b squared looks to me like it's, that can't be right, huh? Sorry.
I would say that the answer is 8 in this example.
I think it's 8 times A bracket B.
We have four terms coming from these 4 points, and they come with equal sign, and then use this argument. And for general, but in general, we need to we want this J to be 1. So what I times J I minus 1 bj and so on. We have I factorial j to the power I factorial j factorial j to the power I something like that. By they claim that the answer will be some determinant. They mean that, maybe they mean that there will be some signs -1, but I don't see this -1s in these computations. The formula for general case involves a determinant. General case, they mean that the general case they want us to compute the general case, which is A times I, B times J, A times H, B times K. This is the general case. And how to, they mean that we, how to draw it. I don't know. Do we need to compute this thing?
Well, maybe next time.
Maybe this is homework.
It was your homework. Okay, yeah, maybe
do you know? Do you think I'm right here?
I don't know. I don't see a good way to organize it yet.
But maybe you could write the answer if it's calculated, in general case.
It's given as an exercise with a hint.
Oh, okay.
So we don't know what the answer is.
No answer.
For the identity traits or
Okay, well, we can think about it.
Yeah.
There
Let's.
should be a nicer way to organize it.
But in the end, it is just the commutator of A and B with just some code. Yeah.
Yeah. Some number.
Okay.
Can you repeat very first calculation of commutator A and some power with B?
Mm-hmm. Here, we.
Just for I to go to, but with good picture.
Mm-hmm.
So I think in the end, we will see why it's behaving like a derivation in this case. It has to do ultimately with interpretation we'll see in terms of functional homology and functional cohomology. So in this case, this space will turn out to be isomorphic to the first functional cohomology of this algebra. This algebra is just one optional else. So the first functional cohomology is just vector fields, and this will be, I think, just the bracket of vector fields. And these are kind of the coefficients in front of the standard vector fields like di by di A and di by di B.
It's a reason to some power.
These, well, I have to write down what the isomorphism is, but my naive guess is that they are just the coefficients in front of partial derivatives. And it could be something more complicated where you have to contract first against something and then maybe lose a power or something. But let's think about it more and try to find a good way to organize it. I don't think we need to torture ourselves at the moment.
No, say it again, please.
We can stop for today.
Let's torture ourselves later.
Do we know how this thing works now? Do you know how this thing works? If we want to do this next week?
Well, I really want to do this next
Well, there are some people not even in Moscow, in China, who ask.
Ah, like this thing.
Yes,
Yeah, I think I.
I meant the video.
No,
I didn't mean the bracket, I meant the video.
Well, yes, I agree with this part, but do we want to finish this calculation?
No.
My sentiments as well.
I mean, I would like to understand the calculation, but we don't need to repeat it on the chalkboard.
Chris, could you come to my room when
Just wrap up.
there are a few things
I got an email